Okay, so this is the second section of chapter 3, so 3.2. It's on Rolle's theorem and the mean value theorem. So these theorems are kind of talking about how you can use the derivative to give approximations. So Rolle's theorem is when you have f be a continuous function on some closed interval, and it needs to be differentiable on an open interval. So if you have that f of a equals f of b, okay, so that means wherever it started, that y value is equal to the y value where that interval ends. Okay, so for example, in this one, we have that f of a is here, f of b is there. Okay, so f of a is equal to f of b. So where you started and stopped, it was the same y value. And then it needs to be continuous in that interval, including at the endpoints. And then differentiable, okay, remember continuous means that you can put your finger there, there's no gaps, there's no holes, there's no asymptotes, that's continuity. And then differentiable means you don't have any jump discontinuities, you have to be continuous first to be differentiable. And then you don't have a cusp, and you can take the derivative anywhere along that curve, but not at the endpoints, of course. So then if your y value is equal at a and at b, then there's at least one number in that open interval where the derivative is 0. Okay, so remember that the derivative being 0 means that your slope of your tangent line is 0. Okay, and if your slope of your tangent line is 0, that means that you're a horizontal line. Okay, so it's saying that if you have some value where your y value is equal to your other y value from either end, then somewhere in between those, you're going to have a horizontal tangent line. And so remember that a horizontal tangent line from 3.1, what we did last time, meant that we had some sort of relative maximum or minima possibility, and that's an important thing for us to know. So if we have an interval where our y values are equal, then we know, okay, it doesn't have to look like this. This is just one example. But in order for these 2 points to be connected, you don't have a ton of options. So this option that's illustrated for you here goes like that. Now that's not the only way that you could connect those two lines. I mean, you could just be a straight horizontal line. Okay, or you could be like some squiggle over here, that they connect. So somehow you have to connect these two values. And if those two values are equal, then you know at some point with those, with that function, that you're going to have a tangent line equal to 0, or sorry, your slope of your tangent line equal to 0. So if you are this one up here, then they showed that in the illustration. That's the derivative set equal to 0, which graphically we interpret that as the slope of the tangent line is 0, which means that the tangent line is a horizontal line. Okay, so that's true for that one. This one where I sketched in the horizontal line, okay, if that was your f, okay, and your f of a is equal to f of b, because everybody's equal to that same y value. If you're a horizontal line, you're constant. Okay, so then that, of course, definitely at least one, you would have an infinite amount. Okay, that tangent line would also be horizontal because the original is also horizontal. And then this one here, it looks like it actually has a couple where it's going to have a horizontal tangent line. So there, somewhere around there, and this other minimum there. Okay, so no matter how you draw this red function line, you're going to have at least one spot in that open interval where you have a horizontal tangent. Okay, so you can kind of mess around with that and kind of see that that is true. If you are playing around with a whole bunch of different red functions, you will at some point in that interval have a horizontal tangent line. Okay, and so remember that from last section, this was very important to us because where your derivative is equal to 0, those were your critical numbers, and your critical numbers are very important in this chapter because that is allowing you to find some extrema on your interval. Okay, so that's Rolle's theorem. And the next theorem we have is the mean value theorem. Okay, so the mean value theorem is saying again that you need to be continuous on the closed interval, differentiable on the open interval. Then there's a number c in that open interval such that, okay, an f prime of c, okay, that's your derivative, okay, so the slope of your tangent line, okay, is equal to this mess. This mess looks like algebra 1, yeah? You have your f of b minus f of a over b minus a. That's slope. Okay, so it's saying that at some time your derivative of c, okay, is equal to the slope, okay, from a to b. Okay, so if we have that illustration, okay, we have this is a and this is b. Well, this is algebra 1. That's just saying take the slope. Okay, and so that would be this. And so that's, of course, a secant line, right? It touches twice. Okay, so that's your secant line, okay, which is just, y minus y over x minus x. That is algebra 1. Okay, it's saying that at some point, okay, in that interval, if I find the slope of my endpoints, okay, which is a comma b, somewhere on this curve, I'm going to have a tangent line that has that same slope, right? So this part is calculus. Okay, so we're saying if you do the algebra part of this problem, you take the slope for the line that would connect A and B, okay, we would get that value. Well, then in that same interval, no matter what your f looks like, he might be some sort of like squiggle up here, he might be down below somewhere, wherever your f is, there's going to be a tangent line that is equal to that number. And so remember that that guy is f primacy, that's your slope of your tangent. This one is slope. So if your slopes are equal, that means you're a parallel line. Okay? And so we know, cool, from the mean value theorem, we know that if we take the slope of these endpoints a, b, then at some point in this interval, we're going to have a tangent that is parallel to that. Okay, and there he is. Okay, so depending on what your f looks like, you'll have a different looking picture, but you know that if you take this slope from your starting point and your ending point, somewhere in this interval, you're going to be equal. And so this has some really cool uses in calc. So, and I wrote some of them down here. So the mean value theorem is used to prove many other theorems. Okay, it's very useful in that way. And then geometrically or graphically, what this is guaranteeing is that there's a tangent line that is parallel through a secant line. Okay, and what that actually means is the tangent line, okay, that's calculus. This is your instantaneous rate of change, right? And then your secant line, that's algebra 1. That's your average rate of change. Okay, so if you have a function that's continuous on this interval, then you know that your average rate of change, which is the red, is equal to the instantaneous rate of change, which is the green. Okay, so you can always find the average rate of change. I mean, you were able to do that years ago in algebra 1. Okay, so if you can find that, then you know that there exists a spot somewhere, you don't really know where, but somewhere on this interval that your instantaneous is actually the same as well. Okay, so that's a very useful thing, and we'll use that in one of our examples today. All right, so we're going to go through some examples. So remember, Rolle's theorem is where you have these two endpoints, and you're saying somewhere, if these two endpoints have the same y value, then somewhere you have to have a horizontal tangent line. Okay, and then the mean value theorem, okay, it's called mean, because mean is the average, right? So that's average rate of change. So your average rate of change is equal to your instantaneous rate of change somewhere. Okay. All right, so your first example is to verify that the hypothesis of the mean value theorem is satisfied. Then find C. Okay, so first we have to figure out who the heck that is. So who is our hypothesis for our mean value? Okay, so remember from geometry that your hypothesis is the part with the if, right? So if f is continuous and differentiable on a b, okay, that's our hypothesis, then blah, 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 that's our conclusion. Okay, so we need to verify that that hypothesis is satisfied for a is 1 and b is 3. Okay, so before we get to use the mean value theorem, we need to show that it's okay to use the mean value theorem. So the mean value theorem is valid if f is continuous on the closed interval and differentiable on the open interval. So we know how to prove that. Okay, there are those 3 steps of continuity, and we had that in our chapter 1. Okay, we also know how to find that something is differentiable. Okay, lucky for us, this f is a polynomial. Okay, and so our hypothesis for this theorem is that it's continuous and differentiable. And so since it is a polynomial, we know that it's continuous and differentiable everywhere. We don't even need to worry about this specific interval. Okay, so we do need to write that we know that it is okay to use the mean value theorem because the hypothesis is satisfied. So you can say that in a few different ways, but we need to say that since f is a polynomial, okay, we know it will be continuous and differentiable everywhere. Okay, and so we know that it's going to be continuous and differentiable everywhere, and you can say that a little bit more specifically by actually saying it'll be continuous, and we really do only care about it being continuous on 1, 3, and differentiable on the open interval 1, 3. Okay, but since it's a polynomial, we know we're definitely set for that. All right, so then we verified that the hypothesis was satisfied. Now we need to find C. Okay, so we are finding that value where, hey, our average value is equal to our instantaneous value. Okay, so they're asking you, where is that happening? We know that it exists, but now they're asking us, where does that happen for this function here? Okay, so first we need to figure out who is our average value. That's our algebra 1. Okay, and so we know we can do that because we've all done algebra 1. And then we'll work on, okay, then what is our instantaneous rate of change? Okay, so first work on your average rate of change. Okay, so our average rate of change is f of somebody minus f of that, right, y minus y, over x minus x. And so we need our values. So who are we actually looking for? We're at a is 1 and b is 3. Okay, so it's going to be f of 3 minus f of 1 all over 3 minus 1. Okay, and so that's our algebra, okay, our average rate of change. And so we can find that pretty quickly. So our f of 3, okay, when you plug in f of 3, okay, and then you plug in your f of 1, okay, you're going to get 14. And then 3 minus 1 is 2. So then we know that that is 7. Okay, so that was our average rate of change. Okay, and so the whole idea now is, okay, so now we want to find where is the instantaneous rate of change equal to that. So we know that this was 7, and this, remember, it graphically is your slope. Okay, so it's the slope of the secant line. Okay, because that was the average rate of change. Now we're trying to find the slope of this green line here. Okay, we know that it's supposed to be 7 because we know that we're finding where is that, where it's going to be equal. So where is this instantaneous rate of change equal to 7? Because we're trying to see where is this average equal to the instantaneous. Okay, we know that the value of the slope is supposed to be 7. Okay, so we say, okay, that needs to equal f prime of c. And so remember, That's your theorem, right? F prime of C is equal to the average rate of change. So we know that the average rate of change is 7 because we can plug numbers in, subtract, and then divide. Yay! So now we need to find our instantaneous rate of change. Well, we can get there. Okay? Our F prime of C is the derivative of F, and so that's 3x squared minus 2x minus 2. Okay? But it's specifically of C. So we know that F prime of x is that, but then plug in your C instead. So it's 3c squared minus 2c minus 2 is equal to 7. Okay? And so we need to find our C. Okay, so we know that, okay, we would like to be able to factor this thing. That's the fastest way we know how to find our values. Okay, so we would subtract the 7 on both sides, right? So we would get 3c squared minus 2c minus 2 is 7. Or sorry, I just rewrote the same thing. You subtract and you get minus 9 is 0. And so now we sit here and we try to factor this thing. And he's not factorable. So instead, well, with integers, so instead we realize, okay, I'm in algebra 1. I'm sitting here trying to solve for C. If I can't factor, what's my next idea? My next idea is quadratic formula. So you plug them in. All right, so I'm opposite of B, so that would be 2 plus or minus square root B squared, that's 4, minus 4AC all over 2A. Okay, so here we go. Plug that into your calc. Okay, and you get that C is approximated by 2.1, and the other value is negative 1.43. Okay, so this happens twice. Okay, so the derivative is equal to 7, which means the slope of your tangent line is 7 in 2 spots on this F. He's equal to that at 2.1, and he's equal to that at negative 1.43. So let's look at that graphically, okay, to figure out what the heck we're looking at. Okay, so we're looking at F. Okay, so F is x cubed minus x squared minus 2x. Okay, and so we want to graph this guy. We know that we're only working with 1 to 3. Okay, so let's make our window kind of accurate with that. Okay, so our window for our x should be between 1 and 3, but let's give it some room so we can kind of see. So I'm going to go 0 to 4. And then our minimums, well, we know that when we plugged in f of 3 and then minus f of 1, that was 14. So let's go for 20, see how that looks. All right, so, oh, we need negatives. Oh, sorry. Okay, so I saw this and realized, oh, what's happening over here? I can't tell. Well, my y's are only positive, right? So I want to see this area down here of my graph, so I need some negative numbers in my y range. So I'm going to go back to my window. So my y minimum, I want to see some negatives in there. So let's just go neg 10. That'll be funny. All right, so now I can see what's happening down there. So this is my F. So I'm looking to see where my instantaneous rate of change is equal to my average rate of change. So I know that I'm talking about where my slope is 7. Okay, so between 1 and 3, well, 1's there, 3's up here, so I can imagine, okay, that's the slope of my tangent is 7, or sorry, my secant is 7. Then I'm trying to figure out, okay, where is my tangent then equal to that? So if I make a little sketch over here, so that I can write on that. Alright, so I hit it 0 at 2, right? And here I'm coming like that, and then I'm going up. I should improve here, but something like that. Okay, so I know that my average rate of change between 1 and 3, so my secant, that slope was 7. And so my whole purpose right now is, okay, so I have my algebra, my average rate of change. I want to find where that instantaneous rate of change is parallel to that. So my instantaneous rate of change is equal. So I want to find, okay, it does kind of look like it's there-ish, right? Because if I'm going up here, that's going to not be parallel. So I'm looking at where it's parallel. So it kind of looks like that, you know, my tangent line here to my graph would be parallel to my secant line right now. Okay, so I'm just looking, you know, it might be down here, but I'm looking for where it looks like those slopes will be equal, which means I'm going to have parallel lines. And so analytically, I did that already. I said, okay, I want it to be equal slopes. So his slope is 7. Make that slope 7. And so I set it equal. I did my algebra, and I said, there he is. He's going to be equal at these two values. Okay, and so does it look accurate at 2.1? So if I did a slope of my tangent at 2.1, okay, so my 2.1 is like right there. So yeah, that, I mean, it's believable. It's not, I'm not proving it right now by looking up at this ruler, but it's believable. Okay, and then my other one is at negative 1.43. Well, negative 1.43 is over here, and we didn't even look at that in our calculator because remember, in this problem, we're looking between 1 and 3. So this negative 1.43 we can not include because it is not in the interval we're looking at. So this guy here, that is not in the interval. Okay, so we're looking for that interval, which is 1, 3 for this problem, and so that just automatically is not part of our discussion. But if our interval was bigger, we would include him, but it's not, so our negative is not in there. So we know, okay, there he is at 2.1. So that's our final answer. So we found C. C was 2.1, okay, or approximately 2.1. So then I can kind of see, okay, so that means if he's at 2.1, he's like there, kind of, okay, around 2.1. And then I can just kind of approximate. So like, what does the tangent line look like? Like, yeah, I would say it looks parallel. Okay, so then that is how you could kind of show it graphically. So yeah, I agree. The tangent line at 2.1 on my graph does look like it would be parallel to my secant line there. Okay, so then we know, we did this analytically, so we know that that slope is 7, and we know that this slope is 7. And so that graphical interpretation is just kind of, just as a check to make sure, yeah, okay, it's believable. I think that that would be true. All right, so then the next problem, okay, is one that we will do together when I return. Okay, so go ahead and make sure that you are done with your homework from 3.1 and then start on the homework of 3.2 that I gave.